approach. And then the other question is how we can see whether we can get such symmetries as remnants of, say, gauge symmetries in some string constructions, in particular in heterotic constructions. And particularly interesting are maybe asymmetries. And in string constructions, of course, there's a natural idea how you get asymmetries as remnants of Lorentz symmetries in the internal space, which naturally would treat fermions different from scalars, for example. And so I'll discuss a bit this in general, and then I give a simple example of an heterotic Z3 orbifold, basically the simplest one you can think of, a blow up to get a smooth Calabi-Yau, and some ideas in the realization of this by a gauge linear sigma model. So the first one is generically, if you have the symmetries will be anomalous, but we can of course save ourselves by Green-Schwarz mechanism, and I'll be very brief. So the general, in 4 dimensions, you have this anomaly polynomial, which is a 6 form, and the Green-Schwarz mechanism requires 3 things. Basically, this one should factorize in a product of a 4 form and a 2 form, and the 2 form is just the field strength of something. So this is just dA, and this A is the anomalous U1. So in 4D, you can say there's always one anomalous U1, and there's an axion field, which is a scalar, which shifts under the anomalous U1. So if this A shifts by delta lambda, then the small a, the axion, just gets this shift. And then you get a coupling of this axion to this x4 field, so this A x4, and then this together with this shift basically tells us that the Green-Schwarz action varies by the descent of the anomaly polynomial, which is just minus the anomaly, so this one cancels the anomaly from the, for example, you get via the Jacobian of the path integral measure. And of course this shift here will force us to write this the Stückelberg type of covariant derivative. So the shift, just the shift of this axion in itself gives the Stückelberg mass to the anomalous U1. So the anomalous U1 is always massive. And of course then the anomaly cancellation requires this shift and this coupling alone. So there's basically two different things here, two related but not entirely the same things. And of course if you have various anomalies, of course you can do the same thing with various axions. So this is basically nothing particularly new. Of course, one can also take a dual description in 4 dimensions. I can take the axion and then I dualize this to a 2 form, which basically says, okay, the axion has a shift which is proportional to this y2 and a coupling to this x4, and this is just exchanged for a 2 form. So this shifts via this x4 and couples to y2. That's basically totally the same thing. In particular, of course, in heterotic constructions or generic supergravity, you get this Karl-Bramont B2 form, and this is as a dual axion, which is the universal axion A0, which is always present there, which is always this is one axion which is always there in heterotic compactifications. And of course, this x4, just by construction, can only contain basically things like trace r squared and trace f squared for various gauge groups, and has a bunch of coefficients. And these are just the anomaly coefficients you would calculate via, say, triangle diagrams. So this is just, these A's would be sum over charges times Dynkin indices or so. And of course, the universal axion A0 is universal because the coupling is universal. So for this A0, there's one distinguished x4, which is basically fixed by supersymmetry, or by the transformation of B2, which is again then fixed by supersymmetry already in 10 dimensions. So this one is the special case of the universal axion, which is dual to this Karl-Bramont B2, which couples universally. So, but in general, from the low energy theory, you can think of these, or there's no need that these couplings need to be the same, or these anomaly coefficients. And this is even true if you have an underlying, say, SU5 symmetry. And so, just take a simple approach where you have an SU5 gut it some way and times some extra U1. Then you can, at the SU5 level, you can just write down these the anomaly coefficients, which are just this one. So there's contribution from the meta. The gauginos contribute if there's an R symmetry. So this R equals 1 would be an R symmetry, and R equals 0 would be a non-R symmetry. And of course, the Higgses also contribute. And of course, at this level, I can just split it in, kind of artificially split this up into the different contributions from the for contributions to the SU3, SU2, SU1 anomaly, and the CH is just the sum of the charges. And now the question is, what does this tell us about the if we break the SU5 to the standard model? And this depends on basically the way of breaking. So if you break by a Higgs mechanism, for example, that's a continuous thing that will not change the fact that these things are the same. A3 is equal to A2, for example. But on the other hand, if you, for example, have an orbifold, if you impose discrete orbifold twists, this will change the zero-mode spectrum, and then this can actually change the anomalies, which also means, for example, if you break the SU5, you certainly kick out the X and Y bosons, and so there's a change in the for asymmetries. And if you also want maybe to kick out the triplets, then you also change them, well, the A3 and A1 in this way, and so you would generically end up with non-universal anomaly coefficients in this case. Of course, that depends a bit on the type of breaking, as I said, and of course, once you do that with an orbifold, there's at no point there's this SU5 restored as a full gauge group. So this one, there's the SU5 structure is given by or is reflected in the rest of the meta coupling, but for example, the Higgses are just split multiplets, so there is no SU5 in that sense at this point. But generically, you can have non-universal couplings at this point. And of course, the for Zn symmetries in particular, this means you have basically more freedom in symmetries. The one thing you keep in mind is that Zn squared or Zn cubed anomalies are not really interesting. So the only thing you have to care about is the Zn g squared. But since these need not be universal, you can actually drop some of these constraints, and you can, for example, forbid all the bad terms, including the mu term, with a Z6, which is not an asymmetry, and this charge assignment, which allows all the Kaber couplings and the Weinberg operator. And of course, that is now a purely bottom-up approach. In certain string models, you might have a certain remnants of universality. For example, if you have an EA times EA heterotic string, and I'll discuss this now. In the orbifold, so just the simplest thing you can think of, T6 over Z3, standard embedding, no Wilson line, so you get a gauge group E6 times SU3, and a spectrum composed of 27s and 3s and 3 bars. So this is the untwisted, these are the twisted ones. And note at the beginning, first, there is no anomalous U1, so the universal axion does not shift under anything, and there's also no Fi term. So in principle, this model is just fine as it stands. You don't need to blow up anything, but if you want to, you can blow up. And it means just heuristically, you switch on VEFs for the twisted states, for these blow-up modes, and this correspond in some sense to volumes of certain cycles which are were hidden in the singularity, which are shrunk to zero size. And if you have all these volumes large, then you're basically not anymore in the orbifold, but you're in some supergravity regime. So you can think of this one as a compactification on some smooth Calabi-Yau with the gauge bundle. And of course, the gauge bundle is then related to the quantum numbers of these blow-up modes, of the things you switch on VEFs for. So in particular, if you do this toric resolution, what you do is replace singularities by certain exceptional divisors, ER. And for simplicity, we just use line bundles. So it's just abelian fluxes, which are only supported on these ERs. And then these HI would be in the carton of E8 times E8, and then there's a certain coefficient vectors, VI, bundle vectors. And for a very simple model, if you fulfill certain consistency conditions, you end up breaking E6 to SO10 times U1 twice in different ways. So you basically kick out this and this node from the E6 Dynkin diagram, and you end up with SO8 times U1s, and the SU3 is untouched in this model. And then the massless spectrum depends a bit on the detailed way of this breaking. And note that this is an abelian flux. So you would think, okay, if this one would leave the U1s unbroken at this point, especially, but this of course is puzzle because on the orbifold, if you switch on VEFs, you would think the U1s are broken. And indeed, they are also here because they are commute with the flux, or they commute with themselves, obviously. But the flux gauges shift symmetries of certain axions along, so basically from the reduction of B2 along these ERs, you get extra axions, and these shift under U1A and U1B. So both of these U1s are massive. So it's clear that even though the flux is actually abelian, the U1s are gone from the spectrum in a Stückelberg type manner. And if you look at the polynomial, actually just the 12, I12, insert the backgrounds, or you can just take the 4D modes and consider the diagrams, and then you get this FA, FB contributions, and you see that depending on these numbers P, K, P, and Q, you can have for example FB totally anomalous, but U1A, for example, always is anomalous in one way or other. And there's one thing, and the other thing is that you see certain remnant universalities, in particular that the non-abelian parts here are the same for both of these U1s, which is the generic feature of these E8 constructions. And the fact that the Riemann tensor is the same, has the same coefficient, is just an artifact here that we have one unbroken E8. This is not generic. Okay, now the remnant symmetries. Okay, for non-R symmetries, it's pretty simple. We have these blow-up modes. Okay, this leaves Z4 times Z4 invariant. Well, at the face of it, you would see that think there's a Z4 times Z4 unbroken gauge symmetry. But the charges are all even, so basically it's a Z2 times Z2 symmetry on the mass spectrum. But the more interesting part is the R symmetry. And there's these R transformations on the orbifold come basically from this H momentum, from these sublattice rotations. The V is basically a sublattice rotation, so it's a rotation in one of these tori. And the then you get certain Zn symmetries, and the conventions are somewhat tricky, but in the end it's a Z18 symmetry, and it's an R symmetry because theta has charge 3 under this one. So that's why some people call this a Z6 R symmetry, but it's not a Z6 in the sense that doing it 6 times gives you back the identity. And then you might think, okay, if I switch on certain blow-up modes, how do I see remnant R symmetries? I seek unbroken combinations of these 3 things, and I also have the U1s, which I can mix into the R symmetries. But if you take a closer look, you see that there's only a Z2 R symmetry, which is trivial, which is not a real R symmetry. So in this sense, you would think the R symmetries are totally broken. And now the question is, how do you see that in the Calabi-Yau approach? And the way we do it is we look at this GLSM description. So basically, we think about this as a gauge linear sigma model, which is just a 2-dimensional supersymmetric field theory. Well, has U1 symmetry, so that's why it's called gauged. And the fields correspond to some coordinates, and the connection to string theory is that you would expect that in the R limit this flows to a conformal field theory. So this is GLSM is not conformal in itself, but you would think it flows to some kind of what you then think of as a worldsheet theory. And so you start out with these this target space basically. So P2 3 is just a torus, so it's a degree 3 hypersurface in a projective space. And this one is just basically T6 over Z3, and to perform the blow-up, you have to introduce what were the exceptional divisors, which in this case corresponds to extra coordinates. So you have a set of coordinates here, and if you introduce new ones, you have to introduce new gaugings to keep the degrees of freedom fixed. And then, of course, you have to turn on the gauge bundle, which are certain superfields, which then have charges under these U1s. And this again is related to these bundle vectors. And then here you can see the R symmetries. So basically, the geometry is fixed by the F and D term equations of this supersymmetric field theory. But then you would see there's discrete transformations or discrete symmetries of these fields, which leave these F and D terms invariant. And these ones may or may not be R symmetries, but the way to detect this is that these are R symmetries if they leave the holomorphic 3 form invariant, because holomorphic 3 form is basically related to the invariant spinor in this way. So the holomorphic 3 form has the same charge as the superpotential. So this one transforms under the symmetry, it's an R symmetry, and otherwise it's just a normal symmetry. And so if you write down this the holomorphic 3 form, which you can do in patches, but it's enough to look at these transformation properties, you find basically 2 types of these R symmetries. One of them is you have just phases. The point is that just from the structure of these P2s, or of these polynomials that cut off these P2s, you see that the Z's only appear as Z cubed. So you always have this phase symmetries. So you would think that there's Z6 R symmetries. And then there's something interesting, because you see that the D terms are non-homogeneous on the right-hand side. They have basically Kähler parameters, which are or the Fi terms of these U1 symmetries. And for certain values, there's certain symmetries which correspond to permutations of these fields. You actually exchange sets of coordinates, and this gives rise to special types of R symmetries. And so the one thing, as I said, is we always seem to have this unbreakable Z3 rotations, because the coordinates only appear in this manner. And that's of course weird, because we saw in the orbifold that we usually break everything. And I guess we think we have this, we can understand this, that these are broken actually by deformations of the Kähler potential. So basically the ones for the gauge bundle. So these, the marginal deformations of these Kähler potential terms. So this is d2 theta, but this is still a Kähler potential term, because it's only half the supersymmetry. And this, so this would be the massless four-dimensional matter, but there will also be some z-dependent terms depending on the charges. And then these ones contain z in different powers. So these ones would be the ones that actually break the R-symmetries generically. And then the nice thing, the geometry comes in, because you know that the presence of these deformations depends on the phase. Depending on what the Fi parameters are, these would usually set certain of these fields to 0, which actually Fabian Rühle will talk about on Thursday in more detail. And then this will allow certain of these fields or not allow certain of these fields. So this will actually control which of these symmetries are actually broken. And we find that generically we don't, again, see no R-symmetry, but if we set these Kähler parameters to this to certain values, then we see that there are enhanced R-symmetries, Z3 R-symmetries, for example. Okay, this brings me to the conclusion. The anomalies, okay, my point is anomalies from the bottom-up perspective, they need not be universal. And there's one particular exception, which is of course the orbifold anomalous one, which is just by construction always universal. And for generic string compactifications, you can have a bunch of axions, and in particular, all the ones which are not the universal one will have non-universal couplings. And if you use them, you can have non-R-symmetries to forbid the mu term. But now in the blow-up, you see that we have line bundles which can reduce the rank, of course, by the axion shift. That's a well-known thing in the heterotic theory. And but we see that we can actually understand how we see this gauge discrete subgroups unbroken, R-symmetries and non-R-symmetries. And the outlook is, the main part is that these the GLSM, the geometry part, has these unbreakable symmetries which seem to be broken by the gauge bundle. And this is something we certainly need to understand much better to really get the handle on this one. This is also again related to the massless spectrum, the four-dimensional spectrum, and this particularly well, not well enough understood for the compact case. I guess for the non-compact case it's more or less known, but for the non-compact case it's not. And then we see some particular type of R-symmetries, which are these exchange symmetries, which only appear at certain loci of the Kähler moduli space. And this is of course very interesting, because for these blow-ups we have the orbifold just to double check the thing, but of course the orbifold blow-ups are just a small part of this Calabi-Yau landscape. So there's certainly, to understand this much better, we can use this for many more generic Calabi-Yaus. All right, thank you.
So I don't understand. You say that your R-symmetries, or your mu term, is forbidden by not an R-symmetry. Your low-energy theory has anomalies, right?
Yeah.
And you say that came out of a theory which had no anomalies to begin with. You spontaneously broke the symmetry, and now you get a low-energy theory which has anomalies, with a symmetry which is anomalous.
No, this is just a purely bottom-up thing. I just say, okay, what up?
Have you constructed a theory which is at the gut scale, which you do
this just
triplet splitting, and then gives you a low energy, which is anomaly free, and then at low energies you get anomalies in your symmetry?
No, well, this, as I said, this symmetry is just a purely bottom-up thing. So we just take the MSSM.
But this symmetry, it has anomalies in it, right?
Yes. So I would assume that there's a.
How do you expect that to come out of an anomaly-free theory, which you did some orbifolding or whatever, and now you get a theory which has a symmetry, you claim, which is anomalous?
Well, I assume that the symmetry, there's an axiom to cancel the symmetry, and then generally I would have.
So your axions live in your low-energy theory. You have to include those states in your low-energy theory?
Yes.
So it's not just the MSSM. You have these axion states.
Yes, yeah, of course. I assume that there's a Green-Schwarz mechanism
in the low-energy theory.
Yes.
But as we discussed, so such settings will in general be not consistent with gauge coupling unification.
That's probably true. Yeah, we didn't look at this, but probably this one would screw up. Oh, that's a, yeah, probably these things might screw up gauge coupling unification, for example. That's one we didn't check.
All right, we better move on. Let's thank the speaker again.